Okay, thank you very much, Igor. I'm very delighted to be here. Obviously, I wish I could be there in person, but that's not the case. I'm sitting in my basement in my house. It's where I've been working for the last year. I'm going to talk to you about bonded particle modeling. First, a little story. I did my PhD way back in 1993 and 95. I joined Itasca. Peter Kundal used to work for Itasca. And I'm sure you all know who Peter Kundal is, the originator of the distinct element method. And I remember I sat down with him when I first came there, and he says, I've started doing this research. I take my discrete element model and I put some glue between the particles, and then I load it, and it looks a lot like a rock when it fractures. He says, I'm sure it's just going to make pretty pictures. I don't think it's going to go anywhere, but would you be interested in working on this with me and seeing if we could actually try to quantify this and compare it with rock? Well, it turns out that it does quantifiably behave like a rock, and it's quite a good model, as I will show you, for rock. And I've been a big part of my work since that time has been in the development and in teaching courses and in doing a lot of other things related to this bonded particle model, which is implemented in the particle flow code at Itasca, but it's also implemented in many discrete element codes. Okay, here we go. So I'm going to try to give you an overview of bonded particle modeling. This is all described in the original paper from 2004, and then more of an update to this. I did another paper in 2015. Really don't need to be a rock mechanics expert to understand this talk. So let's get started. Overview, I'm going to give you the basic idea of bonded particle modeling. Then we're going to talk a little bit about the microstructural physics of rock. And we're going to argue that this model behaves and replicates most of the micromechanical processes that occur in rock. Then we're going to talk about more detail about this bonded particle model, where we basically have a synthetic material that are grains, and these grains are glued together. This gives us our bonded particle model. And then I'm going to go through a number of different microstructural models that can be provided by using this as the approach. Then we're going to do some examples, show some examples of different applications of this, and then I'll conclude and give some thoughts for the future. Okay, we got to start with a poem. So here's a poem. What's in my journal? This guy is journaling, trying to understand what's going on inside his head. So he says, clues that lead nowhere, that never connected anyway. Deliberate obfuscation, the kind that takes genius. Obfuscation, that's when you make something obscure. It's really not that complicated, but you make it much more complicated than it needs to be. I like to argue that what's in my lecture, clues that spawn understanding, arrived at by modeling. Deliberate simplification, the kind that gives clarity. There really is a need for simplification in rock mechanics modeling, in almost all modeling. What people tend to do is they try to take all of the details of their real systems and try to put every single thing in a model, and oftentimes then the model gets kind of unwieldy. What's really important is figuring out what are the essential features of your system and what is it that you want to get from your model, and then try to build the simplest possible model to achieve that. So what's the basic idea of a bonded particle model? Here's we will idealize a rock mass as a whole bunch of intact rock that has joints going through it. Okay, the overall mechanical behavior of this system arises because you have interactions. You have two things going on. You have the microstructure of the intact rock, and then you have these joints that are overlaid on top of that. So the intact rock can fracture, break apart, and flow, and these joints themselves can begin to rupture and slide. Okay. The bonded particle models that we build mimic this system of intact rock and joints. And the overall philosophy here is that the closer we can match both the microstructural and the structural features, the closer we're going to match the actual macroscopic behavior. Here's an example. So we're going to say, we think of this as, I'll call the intact rock a base material. What we have here in the very light green is approximately 100 by 100 discs of slightly different radius that have been packed together to begin with. Then these lighter green lines are evenly spaced joints. We have a particular contact model that we use that allows us to put joints in a bonded particle system such that the bumpiness of the interfaces are removed. And so we really can model the behavior of joints. And so what we've got then is, again, this bonded rigid grains, which is the base material. We have joints, which are the interfaces. So we can have the intact rock part breaking apart. We can have the joints rupturing and sliding. And I just want to show what this looks like if we, what we're doing here is we're compressing this rock specimen, if you will. This is just a 2D model. We're compressing this between these two platens. We're moving them together. We're monitoring the force, dividing that by the cross-sectional area. That's our stress on the y-axis. This is our strain on the x-axis, and here's the stress strain curve. And now these little red lines are broken bonds. And so we see we're getting breakages near the interfaces. They're all kind of homogeneously distributed, and the stress strain curve keeps getting higher and higher. Now, as we get closer to the peak, we're going to start to see more damage. Notice now we're starting to see breakages that are spanning across this, and then we get to the peak, we get the failure, and you can see here with the black lines are the breakages of the joints itself, and that of course leads to the stress strain curve dropping. Okay, so that's the idea of a bonded particle model, okay, and the kind of things that we might do with it. Again, it's a very simple concept. You've got grains, you've got bonds. These grains could be of any shape. They could be in 2D, they could be in 3D. I'm showing the very, very simplest case to illustrate the idea here. Here's my example to talk about what's going on with this system. Here again, we have the yellow this time. We have approximately 100 by 100 bonded discs as the base material. And then we've drilled some holes in here to make this more interesting. And now we're compressing it. And what you're seeing here is the force chains that are going through the material. You're also seeing broken bonds. Because this is cracked here, this thing becomes very compliant. It's not carrying load. In this force chain plot, the blue and the black are compressive forces and the red is tension. And you say tension, it's a compressive loading. How am I getting tension? I'm getting tension because if you have a cemented granular material and you squeeze it, you're going to induce microtension. These are the sort of mechanisms as to why that is. You're effectively wedging apart some of these grains, which causes tension perpendicular to the direction of compression, which then means that if you have some cement in here, if it breaks, what you're getting is when it breaks, it's like you have an axially oriented crack that forms, okay? So what we're seeing here then, notice as I mentioned, this material has unloaded. You're still getting load carried in the center of this system. Now you have these broken bonds which have coalesced into what you could refer to as fractures. These fractures are emanating from the voids. Those were the stress concentrators. And if we can actually look at a movie of this, here's again loading this thing, and we're going to start to see the bonds breaking and the fractures coalescing. That's the stress strain curve that we're measuring. Notice it doesn't drop completely brittly. There's still load carrying capacity even after this is quite a bit broken up. Now we're going to look at this again, but we're going to look at the force chains, which are really the mechanism that explains the behavior. And so again, black and blue is compression, red is tension. Thickness is magnitude. So as we begin to load, it's getting more and more. The loads are getting higher and higher. Notice you're getting tensile stress concentrations above and below each hole, which is what you should be getting. And now watch over here when this fracture forms, this material is going to unload and it's not going to be colored anymore. There you go. Now we're going to see fractures coming up. And notice you're still having residual, you're still having load carrying capacity near the center up until finally you get enough deformation. This, by the way, is how pillars in mines fail. They fail from the outside inwards. So if we try to come up with one sentence to describe rock, this is what we can say. We can think of it as an aggregate of both crystals and amorphous particles, and there's varying amounts of cementing materials in there, right? This is some rock that's 30 meters underneath where I'm sitting right now in Minneapolis, Minnesota. It's called St. Peter Sandstone. This is a cross section. You can't see the length scale. This is 0.25 millimeters. So this is about 2 millimeters across. Here you can see the grains, but if you look closely, it's pretty complicated. There's grains. What about all this material here? Is that cementing material, or is that other grains, or is that cement that's broken? So with this type of modeling, what we're positing here is that intact rock can be represented as a heterogeneous material comprised of cemented grains. Okay, such a system has much disorder, okay, and it's going to be sensitive, its behavior, to all of these different things. How these grains are packed. You could have the same set of grains, but if you pack them differently, you pack them more densely, they're going to be stronger than if you pack them less densely. Obviously, the properties of the grains, the properties of the cement, how much cement you have. And a key element here is that each of these items on the left influences the mechanical behavior, and that it evolves under load application as damage starts to form. If we talk about the brittle mechanical behavior of rock, we typically measure this by doing uniaxial tests, triaxial tests, and some sorts of tension tests. And really, if you want to characterize fractures, there's going to be two types of fractures that we see. We see shear fractures. Here you see a shear fracture that's forming in a triaxial compression test. And then we get extension fractures either from doing a direct tension test, or here we're doing more of what we call these a Brazilian indirect tension test. You squeeze it, you generate tension on the inside here, which then causes an extension fracture to form. The mechanical properties are really controlled by the nature of the pore space of the intact rock, and we can classify rock into two groups here, either compact rock or porous rock. Okay, and there's some examples of those two. The damage that we start to get manifests itself as inelastic volume change, either dilation or compaction. And this is happening because there are microstructural changes that are going on before you actually reach the full-scale macroscopic failure. So if you had a granular aggregate and you apply deviatoric loading, you get dilatancy because the grains are repacking. If you have a compact rock, you get dilatancy because there's micro cracks that are forming. It's a very, very low porosity system, but you get these micro cracks which cause dilation to occur. If you have a porous rock, it's much more complicated. Even under hydrostatic loading, you can get the grain crushing. It'll start compacting. Under deviatoric loading, you can do the same as a compact rock. You can get dilatancy, but you can also get compactancy, where you start getting grain crushing and collapse of the pores. When one of the things that why they measure this is they see something called shear enhanced compaction. And typically we describe the compressive behavior of rock by looking at stress strain curves. This curve up here is axial stress. Here's axial stress versus axial strain. Here's radial strain, and here's volumetric strain. And people talk about classifying the behavior into three stages. Your initial stage, you can see the hardening in the stress strain curve. This is due to crack closure. There's often small cracks and flaws to begin with in the rock. Then you have a relatively elastic portion where there's not much going on. Then you start to get stable crack growth. As you load a rock in compression, you get axially aligned breakages, and they start happening homogeneously throughout the specimen. You get to a certain point, which they call the crack damage stress. You get a reversal in the volumetric strain. It basically is a huge acceleration of the dilation that starts occurring. And then, of course, you reach the peak. So we can describe it by looking at the stress strain curves. If we want to explain it as to what's causing it, we talk about, well, the rock starts out with having flaws and heterogeneity on the micro scale. Okay, and what we're doing then is we're getting more and more damage and eventually getting localization of this micro cracking. And if you want to do theoretical developments about better understanding these physics, it's important that you have some sort of a realistic structural description of the rock, either a theoretical structural description or a numerical structural description. And such a description has to consider that that there is evolution. The structure of the rock is changing as you're loading it, and you're getting a progressive failure process. So I'd like to argue that bonded particle models actually provide you with a micromechanical theory of brittle failure, because you can construct various physical models of this brittle fracture process. And if you do these, run these models carefully, you can discern then the effects of the microstructure on the macroscopic behavior. So let's try to get a little more handle on this type of modeling here. So all models are idealization. So if we want to idealize rock, let's talk about two different ways to do it. One, we're going to idealize it as a cemented granular material. And as we've said before, when we compress that, we're going to induce microtension, and we're going to see damage in the form of bond breakages. Another way we could idealize the rock as what we call a linear elastic fracture mechanics material, which is a linear elastic body with an initial population of cracks. Here's a crack, it's being compressed, and what's going to happen, it's going to start to slide, and you're going to get these wing cracks that are going to form. And so here the mechanism is because of the wing crack being oriented, you get microtension at the tips, and then you start getting crack extension by these wing cracks forming. So let's try to apply this model to explain why we get axial splitting. When you do a compression test with no confinement, the rock typically splits parallel to the direction of compression. And we say that it originates from these local transverse tensile stresses that you get at the flaws and the heterogeneity. So for both of these idealized materials, you get axial splits that are beginning to nucleate. They're nucleating as wing cracks in the LEFM material. They're nucleating as broken bonds in the bonded particle material. And then these things start to grow into an orientation parallel to the direction of compression. In the LEFM material, there are those lengthening wing cracks. And in the bonded particle model, there are more broken bonds that will eventually can coalesce into extension fractures. The bonded particle model, notice, is allowing microcrack nucleation as well as growth, okay? And it provides a rich set of grain scale discontinuities that can be related to the microstructural features. We can build rocks with particles that are densely packed. We can build rocks that are much porously packed. We can build those things directly in as microstructural features of this type of model. And the key thing here is that you don't need to take the initial rock with its grain scale discontinuities and map that into an initial population of cracks. The other model, you just have to start with the cracks and then you go from there. In this type of modeling, the linear elastic fracture mechanics behavior is itself just an emergent feature of a bonded particle model. And so again, the argument here is that the closer we can match those microstructural features, the closer we're going to match the macroscopic behavior. So this bonded particle model, my work has been involved in using this in the PFC programs, particle flow codes. And what we're doing there is simulating the movement and interaction of these particles using the distinct element method. I'm assuming everyone in the audience knows all about that. And here's your simple case of a box, particles under gravity. These are contact forces with thickness proportional to magnitude in green. You can see how the forces are bigger at the bottom than at the top. We use a soft contact approach whereby we have rigid particles that don't change their shape, and then we put springs in at those contacts. What do we mean by a soft contact approach? Here's a United States. I play a lot of and watch a lot of baseball. There's a baseball. Let's imagine that I was able to balance on two baseballs and then push down on them. So in reality, these baseballs are going to contract and expand, as you see here, okay? With our soft contact approach, they don't. If I go back and forth, you see the difference here. With the soft contact approach, their particles are rigid, they keep their same shape, and then we start to have overlaps at these places. At these overlaps, we then put in springs. So all the deformation is occurring at the overlaps between these bodies. This is actually a very good model for something like a sand made up of quartz grains. When you squeeze that and apply it, as long as you're not at the point where the grains are breaking, again, most of the deformation is occurring at the movement and rearrangement at those contacts, and the amount of deformation of the grains is negligible compared to the other deformations. This would not be a good model for marshmallows, for example. So we have four basic entities. We have these things called balls, which are spheres or discs. We have clumps, which are collections of those. By using more and more balls in your collection, you get a closer and closer representation of a certain shape. We also have things that we call rigid blocks. These are convex polyhedra with rounded edges. And so we have these objects, and these are the objects that interact with each other. They obey the laws of motion. We have walls that are basically surfaces that you can move. And then these things interact at these contacts. And at a contact, you can have a micro force and you can have a micro moment that acts on the two contacting bodies. Here we're pushing these discs together. These again are the contact forces that you see. So what sort of microstructural models can we build with this BPM approach? We're going to talk about this in terms of this idea of having a base material for the intact rock, and then we might overlay joints, we might make voids in there, we might identify different material regions, and we'll talk about all these in a little bit. Again, so we've got this rigid grains joined by deformable and breakable cement. The grains could be balls, they could be clumps, they could be rigid blocks. And this cement, then there's going to be different types of contact models that are going to form the cement of varying degrees. These are going to be of varying degrees of complexity. And for most of these models, when the bond breaks, the behavior reverts to being what we call the linear model, which I'll show you in a minute, which is just a frictional model. So here the grains can be balls and clumps. Here we're showing just a bunch of balls pushed together. There's the cement, there are these black lines. These are clumps of different shapes. One thing you notice right away, you get a very different packing, you get a very different coordination number, everything else as soon as you change the shape and it's no longer a sphere or a disc. We can do this with rigid blocks. This is a cylinder to begin with. It's discretized into tetrahedra that perfectly fill the space. Then we can bond those things together. This would be a typical set of axial stress strain curves from triaxial tests on this. And you see that you get increasing strength and increasing residual strength as you increase the confinement. We see the same effect. Here's a case of Voronoi shaped grains that are perfectly filling the space. We bond those together. And again, we're seeing this effect of confinement on the differential stress. So again, we can really, the type of model, the type of PFC material is going to depend upon the type of contact model at those contacts. So let's start with the simplest contact model where there is no bonding. We call this the linear model. For those of you familiar with distinct elements, here's the paper that everybody refers to, the Kundal and Strack 1979 paper. You know, Peter wasn't even really interested in writing a paper, but Otto Strack was in the department with him and said, this is pretty interesting stuff. I think we should write a paper about this. Otto Strack is still in the department. Peter Kundal is retired. You know, Otto Strack does groundwater flow and things, but he's associated with the beginnings of the distinct element method. So this model is quite simple. Here I'm going to show it as two surfaces coming into contact. There's a very small surface over which they're touching, and there's going to basically just be a force which we can decompose into a normal component and a shear component. Here we're showing those two little hunks of surfaces, and there's really mainly just three parameters here. There's a normal stiffness, there's a shear stiffness, and there's a concept of a friction coefficient. Okay, so that's our linear model. That's basically for granular frictional material. If we then go and take this concept of, let's just put like a little spot of glue to that system. If we have a spot of glue now, the force, first of all, we can pull it apart and there will be forces that will develop, tensile forces. And so in terms of rheological system, when it's bonded, basically there's a little fuse here that has a tensile strength. And in the shear, there's a little force that's a shear force. Notice that this cannot resist moment, because I say it's a spot of glue. There has to be some width across here so that when you apply bending, you can build up compression and tension on the inside and outside. So this is our simplest possible bonding model. This was the model that Peter had begun exploring when I gave my little discussion at the beginning and saying, hey, I just put some little glue inside. One of the first things we realized with this model, it's quite simplistic and there's no micro moments that can develop. Those are important often if you want to start behaving like a rock. Then we can go to this model. We call this a parallel bond model. Conceptually now what we have is, even though it's just touching here and here, it's as though we have cement in between this stuff. Here's the picture. These are glass beads cemented with epoxy, where essentially mimicking the behavior of that. We're basically saying, in addition to the surface-surface interaction, which is similar to the linear model, it's like you have glue, cement all around here in a circle. You can see the cement is like a circular cross-section beam, if you will, that lies between there. And so rheologically, that looks like when it's unbonded, it's completely broken. It's just the linear model. But when it's bonded, now notice we have two springs acting in parallel, thus the word parallel bond. There's your just surface-surface interaction, stiffness. Here's the stiffness of the cement. And we also have two springs acting in parallel in the shear direction. And the key thing is that after it breaks, it behaves like the linear model. So this cement just like disappears when it breaks. Okay, there we go. Bond breaks, it is removed. It no longer resists relative rotation. That's the other thing. This model will resist micro moments. We also have basically what we call a soft bonded contact. This is the parallel bond, but it also has tensile softening. Okay, and when it's unbonded, it has rolling resistance. And so here's just showing the tensile softening. This is a tensile stress being carried in the outer fiber of the bond, and you can see this, and this is elongation in that outer fiber, and you basically get it loads up. Instead of just breaking brittly, we can control the slope of the unloading here. Okay, so this model is not as simple. You don't just get a breakage where suddenly everything goes to zero. You're getting a softening response. Then we ended up developing another model, which we call a flat joint contact. What this is we essentially make this behave like we have surfaces of some width here. There's some radius, if you will. And then we're going to discretize each of these surfaces into elements. Okay, and now each of these elements is going to have a simple bonding concept like a contact bond. So we discretize into the elements. They can be initially bonded. After they break, they're frictional. This is what these models look like. Here's a 3D one, here's a 2D one. So even though you have discs, if you put this flat joint model in, you're going to resist moment. Okay. Here's when it's beginning to fail. Here's hold this one steady, rotate this one. These are broken bonds that are in red. You can see it's breaking on the tensile side of the loading here of the interface. And this is what it looks like in 2D. You can't really see this very well, but only 3 of those 4 guys are cracked as it's beginning to bend. So we've got partial damage that can occur in this model. And also, even after it's fully broken, it still resists rotation. So here, this is an example of a system. It's fully, there's no bonds even to begin with. We keep the outside balls fixed. We rotate this, and you can see these are compressive forces that are developing on these edges here to keep this thing interlocked. Okay. Let's go back to talk about some of these microstructural models that we can create. So the first way, we can overlay joints on the base material. Let's talk about how do we put these joints in here. What we do is we make a collection of what we call smooth joint contacts. So these contacts here, which are the ones between discs on opposite sides of the desired joint, are going to have a special contact model so that instead of behaving as though the surfaces were oriented like this, it's going to pretend that the surfaces are oriented like this and that this has been cut off. Okay, so you can work all this out, and so now you have a contact model. This can be initially bonded. After it bonds this, after a certain stress, it can break, and then it's frictional. Okay, this eliminates that inherent bumpiness. If you just put simple bonding between the guys on these contacts here, when you tried to shear this interface, you would have this bumpiness. With this model, you can actually put in the joint properties and it removes that bumpiness. So this is what this looks like in 3D. You get this cloud of these things on both sides of the desired joint. And here's what this looks like. Here's a 2D model. Here's a 3D model. This is a fixed bottom. We have gravity on. There's no bonding here. There's just a friction coefficient of 1 and it's stable. We change the friction coefficient to 0, and you can see this can then slide. So this is a way that we can put joints into a bonded system. And we're going to see that's going to be used in some of these models. So another way people have, another type of microstructural model is where we can take a base material that's of glued bonded things, and then we can put in holes. This is actually some work that we did for Yucca Mountain, which was the proposed site of nuclear waste storage in the United States. And this is the looking at a photograph of a tunnel, and there's all these voids in the rock, and they've been identified here. And so what we could do is map those voids into voids here, and we could get stress strain curves as though we had done a test on this material. We did this for a large number of sample points along the tunnel to try to get some idea of the effect of those voids on the strength and stiffness properties of the actual rock. It was not possible to do compression tests on this because many of these voids were much too large. Here's another way we can do this. This is work by Tatiana Katsaga back in 2010 for her PhD at the University of Toronto. This is a concrete specimen, and you can see what's been done here. We start with a bonded assembly in the background, and then here's an aggregate piece. So we make all these guys part of that same group. We give the aggregate different properties than we give the mortar. And here she's doing a comparison of the broken bonds and the damage that was seen in the test. We can now, because we can put these joints in, people have done work where they create what they call a synthetic rock mass, where you just put large numbers of these joints that correspond with the jointing that you see in the actual rock. Okay, you can get very complex systems with this. And these sorts of models are used to study the impact of the joint fabric on the strength, on the brittleness, and on the fragmentation. This is done at the rock mass scale. Here's actually a poster that I have in my office that we created some years ago. And if you look, you can see the joint fabric. There are 8 joint sets that have been overlaid on this bonded system. Here's a close-up of the upper left-hand corner. Here's another way. This model is going to apply at the actual specimen grain scale. This is what I call a grain-based model. It's the same idea. Let's assume you somehow have a grain structure. In this case, this was a Voronoi packing. We can superimpose that on top of a bonded assembly of discs. And then again, at all of these, we treat these as joints and we put in smooth joint contacts. So here we have parallel bonded material for the intact rock and smooth joint contacts here. And again, this system now, because it's going to progressively break around here, is really allowing partial damage and grain breakage. I'll come back to that in a moment. Now I want to just go through some examples relatively quickly. Here's some work that we did. This was a parallel bonded system in 2D and 3D of spheres. These were spherical beads. And here we're doing a compression test, and you can see the axial fracture largely that has formed. They actually formed in 2 directions. You can kind of see the other one here. It was interesting when we take this system, we do this, we get a Hertzian response because this, when it's bonded, behaves very much like a linear elastic isotropic material before it breaks. And then this work was being done to determine breakage stresses of both solid and hollow beads. Here's some work that was done to try to understand the effects of the strength of cemented backfill. In a mine, you often make these big, huge things called stopes. Look at the length scale here, that's 35 meters. This would all be removed, this material up above. You don't want to leave those openings in the mine, so what you do is you put in cemented backfill. After it's cemented, you come a little bit lower and you excavate more. And so this is looking at, by building bonded material that had different amounts of unconfined compressive strength, you can see when you do an undercut, in all cases of 15 meters, as the rock gets weaker, you see bigger amounts of breakage above that. Here's just a movie of that. Here's the 15 meters. And in this case, the UCS of this material is only 0.5 MPa. And so in this case, this rock fill is so weak, you can see the bonds are just breaking and it's turning into a granular material. If I run this all the way, the whole thing will eventually pile down. So that's with a 0.5 MPa UCS. We build the exact same material, but now we give it a 1 MPa strength and we undercut it. and now it has enough strength such that it only locally fails, and we get this material, this back that forms, and it's a stable back. Okay, so this was used to do a big parametric study to try to understand what sort of rock fill strength would be needed to be able to have stable things when they've done different size undercuts. Let's go back to this thing here. It turns out that for many years, we only had the parallel bonded model. And it turns out with these parallel bonded discs or spheres, you cannot match the high ratio of compressive strength to tensile strength for compact rock. Granite has a compressive strength about 200 MPa, tensile strength of about 10. So the ratio is about 20 or more. When we build parallel bonded discs and spheres, we could never get such a high ratio. We find now that you can overcome this limitation if you somehow introduce intergranular interlock, okay, and have a well-connected grain structure that can sustain partial damage. And so that was actually what led to the development of this flat joint model. So here's again a parallel bond. This is like the cement. When it's bonded, after it breaks, there's no more cement. It's only a frictional interaction. There's not much resistance to rotation anymore. If you have a flat joint though, and it's broken, these notional surfaces remain, and you have this interlock. So you're getting different. Instead of behaving like this system, it's behaving more like this. This system is going to have, as a rock, a much higher compressive to tensile strength ratio. So let's take a look at this two different ways we could build bonded particle models of that system. This is that grain-based model. So there's a whole bunch of small discs in here that have been glued together, and then there's joints overlaid on top. This is that flat joint contact model. So there's just a disc. So every grain here might have 20 by 20 discs. Every grain here is just a single disc, okay? So this grain is deformable and breakable because it's a full-scale bonded particle model. This grain is rigid. But in both cases, the interfaces here are deformable, breakable, and can have partial damage. And so this is that grain-based material. This up here is a direct tension test, and these are the breakages. And you can see that's breaking in tension, and it's breaking and forming a single fracture. These two plots are, forget the red line, that's an artifact. These two plots are UCS tests, compression tests. And what you're seeing here is partial damage along the edges of these grains. Here we see damage completely where it's broken all the way along the edges of the grains. The damage is oriented subparallel to the direction of compression, as it should. And then when you get near the peak, you start getting what look like little wing cracks forming off the sides, and there's some shear breakages that need to occur because you need to form some sort of an axial split in order to break the whole specimen. This is the contact force chains, and this is showing you're able to see in these plots that this is axial splitting. There's opening going on as we squeeze this. Let's build a flat jointed material and look at that. Here's a flat jointed material that's supposed to represent Castlegate sandstone. This is a cross section of that. Notice the length scale, 0.5 millimeters. The pink is epoxy, which is denoting the pore space in this sandstone. Here's some, if we take that model, here's some of the stress strain response. Castlegate sandstone is solid. The synthetic material is dashed. We're basically getting up to the same as we increase confinement. We're getting almost the same strength on this. And what we're going to see is that the mechanisms we get during both tension and compression tests are very similar to what we see for compact rock, except we don't have grain breakage in these models, and there is grain breakage that's occurring in rock. So let's look at these mechanisms. So here, if we do a direct tension test on the left where we pull this apart, here's the breakages. If we do a fracture toughness test where we machine in a crack, we're seeing growth coming from both tips. If we do an unconfined compression test, notice the displacement field, we're seeing axial splitting. And we're also seeing axial splitting in 3D models. These are bonded Voronoi grains. If we do a confined compression test, notice the displacement field, we're seeing shear bands forming, shear fractures forming. And here's a summary of this. This is unconfined test. This is a confined test on the same material. This is the typical stress strain curves we see in the peak and post peak. In the unconfined case, this drops all the way down to 0. And you can see that if we allow sufficient deformation to occur after the peak, this is breaking up into axial splitting type. These are fragments. Colors are fragments, connected groups of particles that cannot be that are connected by intact bonds. Here you see the beginnings in the post peak here of what looks like maybe a shear fracture. If you keep loading it, sure enough, it forms these shear fractures. This is now a new mechanism that kinematically can sustain deformation. That's why you reach a residual now, and it's not changing anymore. So this is very much like what we see in rock. We see axial splitting unconfined. We see shear fractures forming, excuse me, when you're confined. Just a couple more ideas. Embed this within a larger continuum model. So this was some work that was done where this is not the scale. This is a continuum model for this outer region. This is a stope in a gold mine deep underground in South Africa. This stope might go about 500 meters out of the plane. This is very low. This is about a meter high or less. And what they do is they go to this face and they go and they keep blasting this face all along the whole distance and keep moving this forward. And this is in a very, very high stress regime. The in situ stresses are on the order of 100 megapascals because it's deep underground. It's a very hard rock. We did a coupling here between the bonded material in this region and the continuum material. We essentially identify the particles on the boundary of the bonded material. We then map those particles into the edges of the continuum zones. And what we end up having is that the continuum zones provide the motion, which is applied to the particle assembly. The particle assembly, meanwhile, gives us unbalanced forces that are applied as tractions acting back on the grid. So we have a two-way coupling. This is the type of thing that we see when we do these models. Here's the model, and we advance the stope, here's the model, okay? And so what we're seeing here is we see these these shear fractures that form. Basically, the stresses are so high that when you move this forward, the material, it wants to push in, and so it pushes in and forms these shear fractures. They're spaced at about the same distance as the advancement rate of the stope. They really see these underground. And then when the stope gets really long, we see these tension fractures, because if it's long, this roof is kind of just hanging there and you start getting these tension fractures. So we see this in the continuum material. And nicely, what we also see is we see these shear bands forming in the discrete material and then propagating into the continuum material. And what we could do with a model like this, of course, is you could try to look in more detail at what's happening in that shear band, because you have all the details of the tensile failures, the shear failures, the orientations, things like that. The last thing I just want to show here is some work that was done modeling sandstone perforation failure. So this might happen when you're doing hydraulic fracturing. You go deep underground in your well bore, you go locally and you shoot perforations through the metal casing. These perforations are probably about 50 millimeter diameter, and then it's through those perforations that you can now start to put your fracturing fluid. But now you have these perforations and you would like them not to collapse, so you want to understand that. And so here, if we just load sandstone specimens with holes, and what we see is we see this very complicated damage that starts forming here. The grains are actually breaking near the borehole wall. And what happens if you keep loading this is you get these grains breaking, loosening, and then you start to form these grain fragments. And you can see how here's a fragment, here's another fragment. These fragments form in the perpendicular to the maximum compressive stress, and they call these things breakouts, okay? So we modeled this with the bonded particle model, and what we modeled to simulate, to mimic that sort of a system, is what they call a thick-walled cylinder test, where you take a typical rock cylinder, 50 millimeters diameter, you drill a hole through the middle, and then you put it in a triaxial cell and you just keep applying confinement typically to the outside. And so here's a 2D model of that. There's the bonded system. We're applying confinement from the outside. In this case, we're also applying confinement from the inside. And if we do that, and we keep on loading, we're going to form stable notches. Here's a very crude model with very large discs, and I want to just show you what happens here. This is using that flat joint contact model. So at this point, it's already been loaded up to 30.5 MPa on the outer boundary, and there's already some damage around the periphery, but it has not localized. Red is broken in tension, blue is broken in shear. Remember, the flat joint has a number of elements along it, so you can have partial damage. These guys are just partially damaged around their edges. If we start to increase the load, you're going to see the displacement field, and by the arrows, you're going to start to see more and more cracking. These cracks are oriented, subparallel, so you're getting these fragments then that are going to form. This is what they see in the rock. These are like onion skins, these fragments that form along the side. Again, to explain that, we need to look at the force chains. Black is compression, and the thicker the line, the higher the magnitude. Now watch what happens. You're going to see that you're going to lose compression in here because the material is getting more compliant as it breaks. Notice also that now you're getting the load can't flow here, it flows to the tip. Now watch that tip form, gets really thick. You get high compression at the tip, that strengthens the rock, it shuts down the process. That's why you get these breakouts. So we're reproducing the mechanisms that occur. In conclusion, I want to say that this model is, I would still argue this type of modeling is in a relatively early phase of development. We have generic models for intact compact rock. I haven't seen much work done yet to deal with this situation where you have much more porous rock. Obviously, we want more computational speed. So as we get the ability to do multi-threading and message passing interface with using large clusters of computers, we're going to begin to be able to do more boundary value problems. And that's what I see happening. Much of the work with this type of modeling has been looking at the behavior during laboratory tests and trying to look at, what if we have cracks in there? What if we don't? What if we have initial joints? What if we don't? Doing things like that on laboratory scale. As we get more computing power, we're going to see more and more use of this to do boundary value problems. And what I'm going to suggest is that we want to start to get to the point where we can actually construct microstructures that are appropriate for different types of rock. Different types of rock, when you start looking at it, have very different microstructures. Here's a granite. Looking closely, it's kind of like grains. Grains are kind of polyhedral. And then here's the basalt, which is much more complicated, right? We would like to be able to begin to build microstructural models of that. People have begun work in that area. And really what I just want to stress is that as we do this, as we start making these more complicated models, we want to try to only include the features that we need to get the relevant micromechanisms. And that's again because the guiding philosophy of this work is that the closer we can match that the microstructural features, the closer we're going to match the macroscopic behavior. And with that, I conclude, and I'm ready to answer any questions. Thank you for your attention.
Thank you very much, David. I guess this was an enjoyable talk. Of course, I'm subjective since I have been involved in certain adjacent activities regarding bonded particle models. I hope everyone enjoyed this talk as well, and we are welcome your questions.
Well, maybe a bit of a weird question. You several times talked about nucleation and growth mechanisms.
Yes.
Now, if you have liquids, there's typically also like a spinodal decomposition where something starts to fall apart everywhere under the same conditions. Does something like that also exist in rocks?
Oh, I don't understand. If you have a liquid What did you
If
say?
you have liquid mixtures, then they can phase separate, and there's two processes by which they can do it. They can do nucleation and growth, or they can do a spinal decomposition where it's unstable everywhere.
You mean like a drop of water and how it breaks apart?
Yeah.
And so
But if you have a liquid mixture, they can separate in two ways.
in two ways. Okay, what's the first way?
Nucleation and growth.
Like internal, you mean like internal to the drop?
Yes, if you have a mixture of two liquids.
Okay. Oh, okay. And so the question is, okay, so they can do that, or they can do what? The other way?
The other way is spinal decomposition, where it becomes unstable everywhere and it starts to fall apart everywhere.
Okay.
Does something like that also exist in rocks, or is that it's always nucleation and growth?
As far as I'm aware, rocks are going to fail by the nucleation and growth, because rocks are this collection of these particles, whether they're well-defined crystals or whether they're amorphous particles like a glass-like thing. And you know, those things are yeah, there's going to be growth. There's either going to be little breakages of that cement caused by rearrangements along the grain boundaries, or also if you go down a length scale, there's going to be breakages internal to grains. And of course, we can keep going down length scales all we want, and then we start seeing other mechanisms that are in play. The type of modeling I'm talking about really only goes down to in that first level to the grains, and so we're not seeing that. You can we can go down to the length scale of the nanometers and do the work that Igor has done, but that's a different system. Yeah, that's one interesting thing about this kind of modeling. It really is independent of length scale. People have used these sorts of discrete element models at many different length scales.
Would this kind of approach also work if you simulate like something like tarmac, where you have a gluey material between the grains?
Do you mean the gluing material that also has some kind of softening or something?
Yes, which doesn't suddenly break, which can be extended over a bit of a distance.
Oh, yeah, that's actually why we created that thing we call the soft bonded model that has softening built into it. Yes, and that's important for systems like that.
Okay, thank you.
Yeah. All right, see, there's no people in the room that I can see, so otherwise I could be making eye contact and like say, hey, what do you think? But
I have a short comment regarding the paper about compression of like composite ceramic beads. Approximately at the same time, in 2014, I have written and published a paper on silicon nanoparticles. And I think the content of those two papers is pretty close. It would be interesting to compare.
Oh,
it seems like, yes, we did at the same time something that is very similar.
Yeah, that would be interesting. Unfortunately, we did that as a it's a report which is confidential, but it had to do with somebody who was interested in all sorts of glass beads that were, some of them were hollow, and if they had big assemblies of these and they started loading them, what's going to happen with them in terms of, are they going to break or not? So
okay, I will send you that paper.
That'd be great.
Yeah, I have another question. You talk a lot about concrete, and this is also where the question belongs to, because I once did a bit of research in the direction of concrete, and we simulated concrete flow, so fresh concrete flow, and we had some very viscous concrete, which was nearly behaving like a solid. Would you expect this bonded particle model also to work for something like very viscous flowing concrete?
Well, everything that I talked about here was just in the brittle range largely. I mean, this type of modeling, of course, can handle the flow, right? The issue is, though, if you start getting very large motion, what are the sort of contact models that you put, right? You want to have a contact model that if you had a whole bunch of things with that model, it would behave like that viscous system. I believe that some people have done some discrete element work in that area, but I'm not it's not at my fingertips.
Okay.
So that's the best answer I can give you.
Okay, thanks.
Yeah.
I remember, David, there have been a work at Itasca when someone modeled like a cutting tool going through the rock. And
sure.
In one case, you've got a brittle failure. In the other case, is more like a viscous thing. When
well, it's more like a viscous thing if it's confined. Then it behaves more viscously than if it's not confined. Yes, that's right.
So I have a question. So by viscous, you mean a ductile behavior of the material?
I think that's what we mean.
So it's a ductile behavior. Yeah. Okay.
Yeah.
Another question is the bonded particle model. What is the relation, or how can you interpret the model compared to other models that using cohesion? Is it the same methodology, or there a difference between both of the methods?
So what do you mean by other models using cohesion? Do you mean continuum models, or do you mean other distinct element models?
Other discrete element models. They use cohesion models. They use cohesion force to interpret the stiffness between the particles.
Yeah, you'd have to tell me more. I mean, I know people have done work, a lot of discrete element where they glue together tetrahedra and they use fracture mechanics concepts to put softening and things like that into their contact models. I don't know exactly what you're referring to when you say,
for example,
they're using cohesion.
Yeah, Stefan, he has his model. In his model, he's incorporated the cohesion forces for.
Oh, do you mean sort of like sticky granular materials?
Yes, like adherent behavior.
Okay. Yeah, that's like a whole different class of system than I was talking about. And yes, I'm aware that you guys have done a lot of that sort of modeling. In fact, that's the answer to the concrete. If you want to get it to flow and all that stuff, you would probably want to use something like the models that you're talking about. We also have recently put some of those models in to PFC, but I myself have not had the opportunity to work with those models.
Mm-hmm. Okay.
You can hear my dog barking outside my window.
So that was actually my idea when I was inviting David to our seminar, just to give to our team a little bit different perspective from solid mechanics community. Of course, there is a little bit different terminology. That is, what do we mean by ductility, like viscosity, cohesion, adhesion, etc. Yeah. But essentially, it is kind of interesting which kind of modeling is actually equivalent. And one thing about like these bond models that are used in solid mechanics community is that the most useful model, which is parallel bond model, can transfer moments. And I'm not aware about our cohesion model that also would be capable of transferring moments. And the other difference is, of course, that we talk about in this rock mechanics community, we talk about macroscopic bodies that totally have nothing to do with thermodynamics. And if something irreversible like breakage happens, it's not going to restore again. And it makes it different from like liquid bridging or something like that is going on in our community here.
Yeah, that's a really, let me just say, that's a really good point. Although when you talk about most of your models don't account for micro moments, that isn't true, right? Those rolling resistance models, that's kind of the key element in there, right? Is they're trying to get that in there. But yeah, rock mechanics is very much in the brittle realm, and oftentimes it's small amounts of strain, because you make a tunnel and you want to see, is the roof going to start to crack or not.
But relatively high strain rate, right?
No, not necessarily at all. No, it's typically most of the work that's done is quasi-static loading. Now, some people are using these models also to do like rock blasting, and there now you're getting really high strain rate. Because this is a fully explicit dynamic model, it can be used for those types of things as well. Everything I'm showing you today has been quasi-statically loaded.
All right. Unless there are no further questions, let us thank the speaker. And David, thank you so much for being here with us today. Thank you very much for your talk.
Okay, thank you very much. Thank you for all of your attention.